Hi everyone. So in this next machine learning video, we're going to be talking about work. Maybe not what you expected, but it's a pretty important part of the human experience. So we do a ton of work all the time, right? So I ask myself, what is the role of humans in the future of work? And this might seem somewhat hyperbolic. I mean, you can hear about these outrageous claims that all humans will be out of a job in some X number of years. I think the reality of things is complicated, but there's some element of, truth to the concern that we will be able to increasingly automate the sort of work that's being done today. And as you may know, I have devoted a large part of my life to data annotation, which is essentially the process of having a human shape or improve or clarify a data set to basically give a model examples from which it can learn to do a certain task. So today I'm going to be reflecting a bit on how that sort of work is evolving and what I believe that means for the future of human work and for the future of data annotation itself. So to start off, we have to talk about something called the distribution. So machine learning always tends to get pretty mathematical pretty quickly, and I'm not going to shy away from that. So you have to bear with me in some, high level math, in the sense that a distribution is a way of describing what possible outcomes there are from some process and how likely or often each outcome will happen. So if you do something a bunch of times, the outcomes should be the same as the distribution that you describe. So if you, for example, take two six-sided dices and you roll them, there are some number of possible outcomes. So there are 36 so-called microstates, and then you can get between 2 and 12 as a sum from rolling the two dices. And the sum doesn't take into account the order of the dices, so that's why the sort of number of columns in the histogram is smaller. The distribution is going to tell you how likely is it that you get 2, 3, 4, 5, 6, 7, all the way up to 12 if you roll two dices enough times. So of course, rolling two dices, you can get any of these numbers. But if you roll two dices 100 times, there's a high probability that the average number of outcomes is this distribution. And there's some universe in which it doesn't look at all like that if you roll 100 times, but those events will be rare, right? So that's how a probability distribution works. And there are lots of these. There are lots of different probability distributions. A popular one is the normal distribution. So a lot of human attributes are normally distributed, like age or the expected lifespan, weight, length, whatever. There's a ton of stuff that is supposedly normally distributed. There are usually some peculiarities to the distributions, like maybe they have a skewed tail, which means some extreme events on some end of the distribution are slightly more likely, or maybe it's several distributions superimposed, so you have this like a mountaintop of different high points and low points that maybe fall very closely to a normal distribution but actually have a few peaks that make it slightly different. And a lot of what we've talked about in my first video is the challenge of generalization. So machine learning, the core objective of machine learning is to in a system to handle a task despite not having seen that exact task before. So how can we build systems that are able to learn robust models that can process quote unquote unseen events? So basically, how can we train it on some distribution of events and then hope to run it and handle events that are not described by the original distribution, or not maybe even a part of it. And this is incredibly hard. Especially since not everything has a stable distribution, but some things do. So what sort of work is there? Well, there are certain tasks, and I'm going to be biased towards automated mobility or self-driving cars. So there are some tasks that are stable in their distribution. Like if you're asked to annotate the size and shape and orientation of a car. So at some point, I think we will have solved that task. Like learning the geometry of an object is doable, and it likely won't change so much over time. At least not for that specific object type. Same goes for kinds of physical attributes or physical dimensions. So there are some things that are stable. And I think this is true also for our day-to-day life. I mean, loading and unloading the dishwasher. It kind of behaves in roughly the same way day after day after day. You may at some point buy a new dishwasher, in which case the task might change, but besides that, it's pretty stable. There are probably lots of work tasks you have that are sampled out of a relatively stable distribution. You're not, presented with totally new tasks or totally new examples of the task every day. Instead, most tasks have already, or most inputs have already been seen, and you know how to handle them. However, there are a lot of shifting distributions out there. Basically, events that are not stable, but rather are changing over time. So I've sort of suggesting a few examples here. So first of all, the obvious one is like you can expand your operational design domain. So in the self-driving car paradigm, that means driving in new geographies. So maybe a new city or a new country, or driving in Africa is very different from driving in Phoenix, Arizona, or driving in India is incredibly challenging compared to driving in very well structured, very simple traffic environment. So as soon as you move a machine learning system so that it is sort of out of distribution, so basically the events it's presented with, the inputs it gets to see, are not behaving the way that the data it's trained on behaves, then you will have to add information about how those new events are supposed to be handled. And the same goes for new infrastructure, new regulations, rare or new objects, strange weather phenomenon. There are all sorts of these things where the world is not static. It's constantly and dynamically evolving. We add new things, expectations, behaviors, and we negotiate what the correct interpretation of those are. And we're still in a relatively physical domain here. If you go to the culture side of things, this phenomenon is extremely intense, right? So what is trendy or cool, or what sort of clothes you should wear, this is constantly shifting, and we are dynamically negotiating this in our social environment. So in order for an AI system to behave in a way that is consistent with human expectations, it's going to need to have some sort of feedback loop where it's evolving with shifting preferences. So there's some sort of sliding scale from stable physical things that have a simple, clear answer to the very subjective, cultural, constantly shifting things. And this connects to the post I made about OpenAI rolling back their recent version of 4.0. So basically, the latest chatbot they launched became a sycophant. It became obnoxiously pleasing to the user. And that's a result of a feedback loop where the human annotators who gave thumbs up and thumbs down on answers they got from that model consistently answered that the most pleasing version was good, because they just saw them one by one, and in isolation it might feel like the better option. But if you do that long enough and you then start using the chatbot continuously, it becomes ridiculous, because every time you ask it something, it's going to say, oh my god, that's the most amazing idea ever, And the most hilarious example was someone suggested to the LLM that I have a business idea. I'm going to sell shit on a stick. And the LLM is like, oh, that's such an amazing idea. You should absolutely do this. And it's like obviously a super bad idea. So I think that's pretty funny and quite a good example of why this human AI feedback loop is so important. And I think this feedback loop is equally important in also the self-driving car domain, or at least if you take a slightly wider stance and talk about sort of perception and sensor fusion and embodied AI. So my vision is that everything that moves is going to be autonomous. And I think there will be tons of continuous adaptations to the machine learning models that power embodied AI that we will need to execute somehow. We need some way to provide the necessary amounts of human feedback to these systems such that they behave in a way that is consistent with our expectations. The problem is that reality is extremely messy, right? So speaking of shifting distributions, I just did a quick search in our system for animals, for example. And there are so many blurry images of, unclear stuff at a long distance where it may or may not matter. It may or may not be useful for your AI model. It may or may not be useful for driving the car, but it's actually quite difficult to tell what is important and what isn't. And a surprising number of things are important. So not detecting those or not taking those into account can have catastrophic impact on your system. There's also extreme complexity in reality. So here is a view into a lane semantic task where you have road markings or a road model. So these are all the lanes, the lane markers, the allowed driving behaviors, the curbsides, road delimiters, and there are tons of them. And humans actually negotiate these very detailed and complex things quite robustly. I mean, we obviously regularly break traffic rules, but we recover really well and we can figure out what an acceptable shortcut is and we can negotiate with other drivers. And it's not entirely clear how we accomplish this. Personally, I think we shouldn't underestimate the many layers on layers of complexity and heuristics that are built into our brain. But we're going to get back to that. Finally, I also want to, on this part of I also want to take a moment and share a really nice video that Waymo published a couple of days ago. So it shows some of the rare and safety critical events that they come across. And I'm very impressed by how well their car handles it. So I'm going to play this here. So here we can see the Waymo Robotaxi and there's a scooter coming on the left and it drives across a curbside and bounces in front of the car. Here's a bicycle that is speeding through an intersection. Here's an electric scooter driver that falls and comes dangerously close to the Robotaxi. And you can also notice if you look at the details here how incredibly resolution the Waymo car has in both the LiDAR and the camera. So there is an enormous number of these rare events that you need to successfully handle in very diverse and adversarial conditions in order to have a fully functioning robotaxi. And that's obviously come a very long way in making this possible. So one way to see it, or the way I see it, is that there are some different categories of knowledge and work, and there is some frontier inherent in this, where there are some things that have stable distributions that we can absolutely automate in the long term, where humans may not be required much, maybe ever again. So basic facts about the world, things, unambiguous statements, that stuff will be learned by models sooner or later. Probably sooner, because we're progressing very quickly right now. And then there's a very large universe of unseen data, right? I mean, most things have never happened. Most things also won't happen because the space of possible universes is like astronomically large. So almost nothing happens. And if it happens, it certainly doesn't happen twice. So there are enormous amounts of very rare events, maybe unique events, at least if you look at them with enough resolution. So all of those things, basically rare events that you don't really know how to handle based on the basic facts that you've learned about the world, I think those will require some amount of human fine-tuning. We will need to inform the model about the preferences we have. If there is no, first principle scientific right answer, which is actually true for a lot of things. I mean, a big part of the human condition is that we're constantly faced with questions for which we can't derive a universally true answer. Like I don't think there is any, final answer that will help you all ambiguity or every decision. I don't think that's a thing. I think the world is complex. Life is complex. It's full of choices and preferences and values. So fine-tuning for me, human fine-tuning means guiding systems in cases where there is no universal truth. And then on top of that, it can also be shifting. So even if you at one point, the human, how should I handle this? The human preference is likely to change over time. I mean, we see cultural norms shifting, we see norms shifting, tons of things are shifting. What was acceptable 100 years ago and what's acceptable today, what is preferred 100 years ago and what is preferred today is very different. And that change cannot be, I think, divined from facts. It's a negotiation and a conversation and an alignment of preferences. So why am I talking so much about this? Well, I think that most people tend to drastically underestimate how much of human work and the human experience is constantly evolving and how little is actually static, stable, well-defined. And I think that the stuff that is static and stable and well-defined, we will learn. I mean, that's why machine learning models have learned language. It's because grammar and sort of basic semantics is quite stable. We have a lot of text in English, and it is, in some sense, it has worked the same way for a long time. Sure, individual words change meaning over time, and they are highly dependent on context. But transformers and attention are able to learn very new context dependencies, assuming there is signal in the training data. But if there isn't any signal, it needs to come from somewhere. There needs to be a preference generating source. And it can be anything, but I believe humans will be a good choice because the products will be used by humans. So for the company I run, Cognic, this becomes a very clear and well-defined business problem where at some point in time there is a current state-of-the-art machine learning model that is able to handle a certain distribution of inputs with a certain reliability, accuracy, quality of prediction. And then our customers want to improve that performance to some goal. And typically the cost of improving machine learning model comes down to, can I improve the training data and can I afford enough GPUs? Those are the two main variables. There's some hyperparameter tuning and like basic improvement of the models, but the vast majority of gains are usually coming from either data or compute. So the question then is, what is kind of the marginal cost of improving the data set? And that essentially comes down to how quickly can I find all the deviations in the training data that are incorrectly labeled, incorrectly annotated by a human, and fix those such that once I retrain the model, it gets better. And the other part of improving the data set is, can I collect more data so that I sample more from the distribution? Because you will never get everything. You will get some approximation of reality. Basically, you will get pieces of this distribution of possible outcomes. And if you haven't seen a certain type of event at all, well, then your model won't be able to handle them very well. Unless in some very abstract sense it resembles something it already seen. But the reality of at least sensor fusion is that the number of sensors and the quote sparsity of it all, the rareness of things means that it is frequently hard to find an abstract resemblance between situations. And it turns out that in this process, where you can find these tasks that are maybe stable, provide one particular superpower, and that is their ability to glue things together. So when I listen to, Silicon Valley entrepreneurs who claim they will be automating work and have completely autonomous remote workers or agents, I frequently feel that they are underestimating the amount of ambiguity between tasks. So, what I mean by that is that, sure, there are plenty of tasks in my day to day job and in most people's day to day job that are great candidates for automation. They are examples of stable distributions where when you receive an input, it is usually from the dense part of the distribution, so you've seen it before. It usually has a reasonably well-defined response, so you should be able to train a system to do that task over and over and over again. However, there are a lot of negotiations and alignment issues and preference tuning that are interpersonal in this process. So let's say you're a travel agent. I see claims that in the near future we will have fully automated travel agents where you just describe what you want to do during your trip and it will book it and everything will be fine. Like, I don't think that's the value contribution of a travel agent today. I mean, booking flight tickets is hardly why I would pay a travel agent. I can book flight tickets. And it's not really that hard, and or it might become faster if I have an AI agent, but like, the point of having a human is that we can have a two-way conversation about my preference, where I can inform it about what I want to do, and give me that social interaction and social kind of validation, or to improve my plan or whatever. And you could argue that, sure, this could be automated too. LLMs are able to have conversations, but I'm fairly sure, I may be wrong, but I'm fairly sure there is a surprising number of rare edge cases that emerge in the interaction between a customer and a travel agent. Things that go wrong, airlines that cancel trips, or hotels that are not what the customer expected, or misunderstandings or vagueness that the customer thinks the travel agent is responsible for not resolving. I mean, I can imagine tons and tons of these things. And that's just a very simple type of work, to be honest. I mean, not to be too negative about travel agents, but I mean, it's a relatively straightforward job. Most jobs are way more complex today, or at least a lot of jobs are, especially knowledge workers who invent or innovate or improve things. There is so much gluing things together that comes down to sort of preference tuning and alignment and understanding each other's desires. So when I put all of this together, when I think about the types of work, the stable distributions, the shifting distributions, the unseen data, the messiness of reality, and humans' ability to glue things together robustly, I believe there is a long timeline for humans adding value into AI systems. And I mean, in the Infinity case, I'm humbled before the fact that I have no idea what's going to happen. Maybe there is obviously the risk of like self-improving AI. That's the big question right now for the big fork in the universe, where on the one hand, if we get AI researchers that are autonomous, so basically if we can create an autonomous AI researcher able to improve AI models autonomously with access to enough compute, that could result in a runaway scenario where it gets dramatically more intelligent and there's an explosion in capabilities. And in that version of the future, there is a risk that it becomes unaligned with humans and basically wipes us out. That's the doomer case, right? That's the big existential threat, the long-term existential risk that AI poses. If it becomes self-improving and if it becomes hostile, there is a real problem. And I've thought a lot about whether I should work assuming that's a likely outcome. I've decided, maybe for naive or practical reasons, that I am actually optimizing my life for a version of the future where AI is going to be better and better, but it's not going to be totally autonomous. And I don't think there will be a runaway scenario in terms of an explosion in intelligence. And therefore, I'm not so worried about the alignment problem, at least not on an existential level. So instead, I've decided to dedicate time and energy to build Cognic, the company that I'm founder and CEO of, in order to handle this constant negotiation of preference. So basically, we have developed an annotation platform, which is a set of software tools that are optimized for humans to review and correct data sets. So we assume that there will be some AI system that provides an initial understanding of the data you have. So you collect all this sensor fusion data, camera, LiDAR, radar data, you run your best current machine learning model across all of it, and it's going to be pretty good. But then there will be tons of things that are either very rare or new, or where there is room for different preferences. And the way you design and shape your product, your self-driving car or your robot or your drone, is to shape the training data, to adjust the labels to accomplish certain things or manifest certain behaviors or comply with certain safety cases. Modern machine learning is programmed through their data set. So as long as there is need for more programming, there are new requirements or new expectations on the system, we will need to fiddle around with the data set. And I think there's a strong equivalent or analogy to programming. So if you go back 70 years or whatever, programming was incredibly tedious. You had to basically cards and slide them into some machine, and it was cumbersome, it was difficult, it took a long time, the feedback loop was slow. And then we learned. So we designed the first programming languages like COBOL. I mean, before then it was basically ones and zeros in some sense. That evolved into C, C++, Java. And today we've come a long way in creating more leverage for humans when shaping software. Today the default is you use some LLM like Claude 3.7 and maybe some IDE like Cursor or IntelliJ or something, and you have a conversation with the LLM to shape the code that you then compile into some executable. And of course that means you need to spend much less time in order to make certain changes to the software. But as it turns out, we have not seen any really drastic decline in the need for software engineers. And I think that's because rather than reduce demand, we have increased the number of users for which we can tailor software. So it turns out there are tons of people who have not had perfect software for their needs until today. And the big trend now with companies like Lovable is that anyone can build software for their needs. And I would argue the people who do prompting in these new products are in some sense software engineers. They're just shaping the code using a different interface. Before you had to write syntax, now you can talk to it. There is an analogy to data annotation in this, where at some point, just 7 years ago when Cognic started, you had to do very low level detailed annotations from scratch. I mean, sensor fusion annotations were very manual and tedious. And we knew, and everyone I think knew, that that's not going to be the future of annotation. The future of annotation is that a lot of things, at least those things that have stable distributions and where the tasks are, not changing so much, models will learn eventually. And then the frontier of work is going to be the fine-tuning and the adaptation to detailed use cases and the optimization for certain user groups, which is exactly what software is all about. You see now ever smaller software companies tailored for smaller and smaller user groups. And it's coming to a point where you can essentially afford building software for a market of one person. Lovable is, in some sense, building software for a market of one person. So Cognic is working to increase the leverage that humans have when shaping data sets, which is similar to the impact that something like Claude 3.7 has on software engineering. And we believe there will continue to be tons of fine-tuning and adaptation to shifting distributions, and we're constantly going to get new unseen data coming in from the universe. And sure, a bunch of stuff is going to go into the stable and automated part, but that does not mean we will run out of the need for human feedback. So I'm optimistic about the role of humans in providing knowledge to AI systems. And I would love to talk to people who have different perspectives on this. But this an optimistic take on the role of humans in the future of AI.